Okay, so let's see. Where we left off was talking about methyl cyclohexane. So that's having one methyl group on our cyclohexane ring. And we said that the ratio of equatorial to axial for methyl cyclohexane was 95 to 5. So we said 95% of the time it's going to be in the equatorial position because you avoid the 1,3 diaxial interactions. And then 5% of the time it's going to be in the axial position because then you do have the 1,3 diaxial interactions. And so do you have to have the ratios or the energies memorized from this slide? No. But it says here for this table, which is 1,3 diaxial interactions for different substituents, I would want you to understand that as you increase the size of the substituent, as you go from a methyl to an ethyl to an isopropyl to a tert-butyl. So again, this one is a methyl. This one is an ethyl, right? Just the condensed structure. This one okay, this one here is a methyl. This one is an ethyl. This one is an isopropyl. And this one is a tert-butyl. Okay, these are just the condensed structures here. You should know this. The group gets bigger and bigger and bigger. What happens is that the amount of the equatorial substituent, the amount of it is going to increase until we get to a tert-butyl where there's practically none of the axial, and that's because the 1,3 diaxial interactions are so pronounced. So I just want you to know the trend that as the group gets bigger, you're going to have less and less of the axial substituent. So here it says if you have tert-butyl cyclohexane, this compound, draw both chair conformations. So that's this compound here is what they're talking about. One tert-butyl group on a cyclohexane. So I'm going to start by drawing both chairs. So I'll draw the first chair going this way, and it doesn't matter which one you draw first, and then we'll put equilibrium arrows, and then we'll draw the other chair, which is going to look something like this. Okay, so those are my two chairs. Now, there's no convention for this. I mean, this carbon could be this one, this one, this one, this one. It doesn't matter, okay? However, since we're learning the subject, I do try to keep some kind of continuity throughout the chapter. And the way that David Klein usually does it is the first substituent, he usually puts it in the upper right corner for the first conformation, and then the lower right corner for the other conformation, okay? So they didn't put a dash or a wedge on this bond, so it doesn't tell us whether it's up or down. So it doesn't matter. I'm going to just draw it going up first. So I'll have it up and axial in this position. So there's my tert-butyl group, which is going to be in the up and axial position. And so in the second conformation, it's going to be up as well, but it's going to be up and equatorial. So there you go. There's my up and axial and my up and equatorial. Now, could anybody tell me, is the equilibrium in this case, is it going to lie to the left or to the right? Would my equilibrium lie to the right or to the left in this case? And it's not a trick question or anything. Yeah, it's going to lie hard to the right, isn't it? Yeah, big time. So I'll erase this arrow, and we'll just put a wee little tiny arrow going in this direction. And the reason, and if you looked at the statistics, it says the ratio is something like 9,999 to 1 or something like that. It's because of what? It's because of the 1,3 diaxial interactions that's experienced in this molecule, okay, that are not present when it's in the equatorial position. So remember, if it's going up and axial in the other conformation, it has to be going up and equatorial. Up and axial and up and equatorial. There we go. So what if you have two substituents, okay? So here, in this compound, they're telling us since the chlorine is on a wedge that it's going up and the methyl group is going down because it's on a dash. Now, if the chlorine is going up, remember that the axial positions alternate up, down, up, down. So that means if this is up and axial, this would have to be down and axial, right? Because they alternate and these are two carbons apart, right? If this position was up and equatorial, then this position would have to be down and equatorial, right? And we see that in the two chairs here that are in equilibrium, right? In the first one, the chlorine is up and axial, so the methyl is down and axial, right? Because they're on adjacent carbons. Here, the chlorine is up and equatorial. The methyl is down and equatorial. Now, you can see that in this case, the equilibrium is going to lie to the right as well. Why? Because in the conformation on the left, I have 1,3 diaxial interactions for the chlorine, and then I also have 1,3 diaxial interactions for my methyl group. So there's so many 1,3 diaxial interactions in the first one, it's not even funny. But in the other one, okay, I don't have any 1,3 diaxial interactions in there. So let's see if we can draw both chair conformations for this compound. So if I draw a chair, something like this. So there's my first chair. This will be my second chair. Again, not my best artwork. Anyhow, it'll get the point across. Okay, so what we'll do is we'll say that this ethyl group, we'll put it at this position. Okay, so if we count 1, 2, 3, that means that this carbon is going to be 1, 2, 3 will be this one here. So let's imagine the ethyl is growing. Well, it's not imagine. If it's up in this structure, it has to be up and axial, right? Because up is axial for this one. So I'll just draw ethyl like that, CH2, CH3. And then the methyl group is going to be down on this carbon. So this carbon that I have the black circle on, but the position that's going down, would it be axial or equatorial? And it's not a question designed to fool you or something. Would the methyl group be going down an axial or down an equatorial in this case? So it's going to be going down and it's going to be going down an equatorial in this case, okay? Right? Because remember, these two carbons, or sorry, these two bonds, okay, where they meet right here, they're both on an upward trajectory, right? So the axial position is going to be going up, whereas the equatorial position is going to be parallel, well, it's going to be parallel with this line and this line, and that's going to be going down. So our methyl group is going to be going down in equatorial, right? Remember, axial and equatorial, they alternate. So up and axial, up and equatorial, up and axial. So this one, if it's up and axial, it means down is equatorial. Okay, hopefully that makes some sense. So now when we do the ring flip, okay, that means that the yellow carbon is going to be this one now, and then we count 3 away like this. So if the ethyl group was up and axial in the first one, it's got to be up and equatorial in this one. So we'll draw it as being up and equatorial. And then it was down in the methyl was down in equatorial, so it's going to have to be down and axial in this one. There we go. So those are the two conformations. Could anybody tell me, would the equilibrium lie to the left or to the right in this case? Based off of what I've drawn here. Would it lie to the left or to the right in this case? It's going to lie to the right, isn't it? Right? Because there's 1,3 diaxial interactions in both of them, right? You have the 1,3 diaxial interactions here between an ethyl group and 2 hydrogens, but here it's going to be between a methyl group and 2 hydrogens. And so ethyl is bigger than a methyl, and so the equilibrium is going to lie to the right-hand side in this case. All right, so there you go. So this is, you can see that they walk through the solution here. It gives you a little bit more detail on it maybe, but this is the answer to that question. Okay, so the question is Skill Builder 4.12. So this is Skill Builder 4.12. So I'll skip this slide when we get there the next time. All right, so now let's see if we can draw both of the chairs for this one. So if I draw my first chair, look something like this, okay? If I draw the other chair, it's gonna look something, that's still not good. It's gonna look something like this. Okay, so those are my two chairs. They're gonna be in equilibrium. So we'll imagine that this carbon here is gonna be this one here. So if that group is going up, in the structure where I have, in this structure here, should the methyl group be axial or equatorial if it's pointing up? It's going to be axial, exactly, because up is axial in this position. So we're going to have a methyl group going up like this, okay? Then for the other group, which is an ethyl group, it's going to be up. So if this, remember, they alternate. This is up and this is up. So if this one is axial, that means the one next to it is going to be equatorial. So ethyl group is going to be going up. Draw better than that. It's going to be going up like this and equatorial. So now when we flip the ring, the methyl group is going to be going up, but it's going to be equatorial. And the ethyl group is going to be up and it's going to be axial like this. All right. So the equilibrium is going to lie to the side of the one where the methyl group is axial. Why? Because there's going to be weaker 1,3 diaxial interactions with a methyl group, right, than there would be with an ethyl group. So we would have one here and one here as well, right? Ethyl group is bigger than a methyl. And so this one is going to be the most stable. All right, there we go. So we've covered this one already. So going back to the idea of cis and trans, okay? We talked about how you can have an alkene where you have two groups that are identical on the same side, that's cis, and then we can have two groups that are identical that are on opposite sides. We call that trans. Well, cis and trans is not the only time you see. It's not only seen with alkenes; it's also seen with rings. So if we have a cyclohexane ring and two groups are on the same side, if they're both pointing up, then we say they're cis. If one is pointing up and one is pointing down, we say that they are trans to each other. And so what would be the relationship between these two compounds, right? You have cis 1,2-dimethyl cyclohexane and trans 1,2-dimethyl cyclohexane. We call these stereoisomers, okay? We say they're stereoisomers. Why? Because they have the same connectivity. So I'm going to write this definition of same connectivity. So that means they're connected in the same order, but different arrangement in space. Okay, right? It goes carbon with a CH3, carbon with a CH3. Here it's carbon with a CH3. Here it's carbon with a CH3. But are these compounds identical? The answer is no. These two are on the same side. These two are on opposite sides. So same connectivity, but different arrangement of atoms in space. That is what stereoisomers are. Okay, this is going to be discussed in a lot more detail. So stereoisomerism will be discussed in much more detail in chapter 5, but this is kind of an initiation to it. So cis and trans, whether it's with an alkene or on a ring, they're stereoisomers. Again, they have the same connectivity. The order that the atoms are connected is identical, but the way that they're arranged spatially in 3 dimensions, so in space means the same thing as 3 dimensions, is different. So that means they are stereoisomers. So if we take a look at the cis compound, okay, cis 1,2-dimethyl cyclohexane, and if you look at these two chairs, okay, if you look at those two chairs, there's no difference between the two. In both of them, you have one methyl group axial and one methyl group equatorial, and so this is going to be a 1-to-1 ratio, right? Because they're identical. But if you look at the trans, in one of them, you have two substituents axial, and then the other one, they're both equatorial. Well, the equilibrium is definitely going to lie to the side where they're both equatorial, and you're going to have very little where they're both axial. And so you have to be very careful on these things when you look at a structure in 2 dimensions and you think, and then you compare it to something in 3 dimensions. We don't cover the section on decalin, so 2 6-membered rings fused together, which you can have cis decalin or trans decalin. It's found in compounds like testosterone, but I'm not going to test you on that. And I also won't test you on all these other polycyclic systems here. However, you might have noticed the chair when you saw the structure of diamond in General Chemistry 1, because you would have studied the different allotropes of carbon, which are, diamond and graphite are the 2 most common, and graphite is the more stable of the 2. But if you make, you guys remember studying covalent network solids? So these are all carbons, all of these vertices here. Every single one of these is a carbon atom. And so you would have seen the chair when you studied diamond. Anyhow, you would have seen it then. It wasn't introduced to you as a chair, but that's the idea. Anyhow, there we go. So that covers all of chapter 4. The whole thing is in the bag. Okay,